Hello, my name is Megan. I'm one of the instructional assistants that teaches at the FSW Math Center. Now, what we're going to go over today is graphing with parent function and using transformations. Now, parent functions, as you can see here, are the fundamental shape of a lot of graphs that we'll be creating. So you might be familiar with something like, say, a linear function. Let's say you have some graph like the function 2x minus 3. Now, from earlier chapters, we know that this is going to be the shape of a line, though the slope and the y-intercept affect where it's located, as well as the direction that it goes. The parent function shows us what the fundamental shape of it is, however, even though we have these two transformations affecting the overall look. So we use the idea of transformations as we will see on the next slide. Now, here an example of the transformations that we can use for a standard parent function of x squared, or a parabola as it might be called. In one such example, we can have vertical shifting up and down. So if one such function looks like x squared plus 2, this represents a vertical shift up 2 units. And so we shift the whole graph up 2 units on the y-axis. A similar transformation can be done in a downward method. So if y squared equals x squared minus 2, that represents starting 2 units down from the parent function and drawing your graph. But that is a vertical placement. We can also have horizontal shifting. For example, let's say that our function looks a bit like this, x plus 2 squared. Since it's interior like this represents a horizontal shift, and because it's plus 2, it'll be to the left 2 units. And so we make our mark 2 units to the left and graph our function. We can also have a shift to the right. Oops. Let's say that y is equal to x minus 2 squared. Now this, instead of going to the left, will be going to the right 2 units. So marking our position point, we graph the function the same as before. So you can have up and down shifting, the vertical shift, and you can have left to right shifting, the horizontal shift. Vertical stretches and vertical shrinks represent some kind of either stretch or compression of your function. So you might, for example, if you have something like y equals 2x squared, at this particular point, you would take your parent function and you would multiply all the y values by 2. In many ways, this will make your function look like it's stretched out like taffy. Similar actions are used by the other transformations. Something else you might encounter is reflection. It could be reflection on the x-axis or the y-axis. An example of reflecting on the x-axis is having your function negative x squared. Since it's exterior of your function, that means we're reflecting on the x-axis. So that means you would take your original function and treat the x-axis as a bit of a mirror. So every x value is still the same, but the y values are now going to be flipped. Y values that used to be positive 1 are now negative 1. Y values that used to be positive 4 are now negative 4. And from here, we're able to make our new graph. In other functions, like if your parent function was, let's say, x, the square root of x, then if you were to have the interior value be a negative x, that would be an example of what it would look like as reflecting on the y-axis. So if your negative sign is interior of the function next to your variable, you're reflecting on the y-axis. Whereas if your negative sign is exterior of the function, then you're reflecting on the x-axis. Now let's try an example. We're going to take the parent function of x squared and use transformations on it in order to determine the different ways that this graph is going to look. So we can do these things simultaneously. There are different orders that we can do this in, but generally what I like to do is begin with the reflections. Now in this particular case, we do have a negative sign outside here. That negative sign takes our function, and as we saw in the previous page, it swaps around every y value for its opposite. So every positive is now a negative, giving us an image like this. So that part's taken care of. The next thing we want to look at in our case is going to be if any compressions or shrinkages happen. And that would be the case here. So we have two representing a compression shrink that we might encounter. Since this 2 is in the exterior of the function, then this represents a vertical stretch. So for the vertical stretch, we multiply each y value by that number, in this case 2. So if your old y value, let's be a bit accurate with it. So originally it looked like this, and then here it looked like this. But by multiplying by 2, this 1 times 2 comes here, 1 times 2 goes here. And this original 4 times 2 becomes an 8, and 8. And so that coefficient of 2 in the front took our blue function, and when we transformed again, stretched it out. The next thing we're going to want to look at is any shifting that happens. And there's two kinds of shifts that we're encountering here. We have a shift here, which represents going to the right 1 unit. And we also have a plus 3, which when we shift that, is going to be up 3. And we can do those in either order. So if we're shifting to the right 1 and up 3, we take the markings in red that were created. We need to go right 1, up 3. And so we do that for all of them. And then this function in green here represents our final solution. So without having to use a graphing calculator over such functions, we were able to use a parent function and transformations to make our own graph of this equation. Now, if you'd like any more help or would like to schedule tutoring appointments, feel free to stop by to our website and at academic supports page, sign up for a tutor. You can also email Sandy Sardinas at fsw.edu in order to schedule an appointment. For any more help, feel free to use our services, which can be found on the website. Thank you.